Alright, so last time we covered the different basic parent graphs and we did a few exercises also on finding their corresponding domains. That's a very important information or tools rather that we need to have fresh for the actual calculus topics when we find limit, when we find derivatives, and when we apply all that to sketch the graph of those derivatives by using not just the properties that we know so far, like functions being even, odd, the symmetry, the domain, but other aspects that we will learn in this course that will even help us give the most accurate graph of a function, whatever function it is. Well, another thing to keep in mind, and I briefly mentioned this last time, that's what we were going to cover today, is shiftings and transformations of the different functions. So, and well, I guess this is nothing new for you. This is something you've seen a few times maybe in intermediate algebra and then in college algebra or pre-calculus. So you have seen it at least once. But we were going to go over every single piece of information again just to briefly review what this is. So number one, we have the first kind of transformations that we can look at are vertical and horizontal shifts. I mean, that's not something new when you look at a function. Oh, x minus 3, the whole quantity square. Well, that's like a parabola shifted 3 units to the right? But now, how do we put symbols and generalize this idea as well? So this is some function f of x, whatever that function is, and this constant c, let's think of it as a positive number, right? So, well, this plus c, whenever you add a number to a given function, for example, x squared plus 5, the square root of x, and outside another plus 5, that means we are shifting the graph, the number of units, whatever that value of c, we're shifting it up. And well, we have the picture here. Let me highlight it with the same color so you can see the connection with each color. So if we start with the graph of f of x, whatever graph of f of x, we're shifting it up c units. The second piece of information here is, well, what if instead we subtract? That means this function gets shifted down c units. If, for example, that value of c is 3, well, we shift the graph of the function 3 units down. If it's plus 3, it's 3 units up. All right, now the thing here is vertical shifts go with the sign, go with the correct sign. Positive is up and negative is down. When it comes to the other shiftings, the horizontal shiftings, we go in the reverse way. Negative means to the right and positive means to the left. And well, this is going to look like this. Let me use a different color to highlight this. Well, so x minus c, that's c units to the right. For example, if c is 5, c, that is f of x minus 5. Well, that's going to shift the graph 5 units, but to the right. And in this case, well, let me highlight it here so you can see. So we can see the connection between the picture and the definition, right? And last but not least, for this situation, well, let me use a different color, something I haven't used. Okay, purple. In this case, the other x plus c, that's going to go c units to the left. All right, for example, if this is x plus 5, okay, that's 5 units to the left. If c is 7, that's 7 units to the left, right? And well, again, The vertical translation, the vertical shiftings go with the sign. Plus means up, minus means down. But in the horizontal shiftings, the minus means goes to the right and the plus goes to the left. So that's the only one that we go in the opposite direction. Those are not the only transformations that we will see. There's a couple more. The other transformations are reflections and stretching, compressing. Well, so as a vertical stretch occurs when we multiply a function by some positive number, a number preferably greater than 1. All right? And well, what's that going to do? Stretch the graph vertically. All right? It's going to output, for example, if we have y equals 2 times f of x, the output is going to get multiplied by that number 2, and therefore that's going to stretch the graph of this function. And well, let me put this in the graphing calculator just so you can see what I'm talking about. All right, and something okay, again, which mode am I? So how about square root of x? Square root of x with 2 times the square root of x. So in this case, that 2 is going to stretch the graph vertically by a factor of 2. That's how we describe it in words. Let's see the graph and confirm. So, okay, that went very fast. So the graph of y equals the square root of x is the one in blue, while the graph of y equals to 2 root of x is the one in red. So we would expect to see the graph in red to be stretched vertically, and our graphing calculator here confirms that idea, right? Of course, you can change your favorite coefficient, 4, 5, and that's going to keep stretching it even more in the vertical way. All right, so let's see if we have something like that. Well, c f of x stretch vertically by a factor of c. And do you see how this graph right here, comparing it with the original, is stretched vertically? And that was also confirmed with the example on our graphing calculator. Okay, let's look at the next point, the next piece of information. Well, what if instead of multiplying by that number, we divide, like in this case? So this is going to be the opposite of stretching, which in this case is going to shrink the graph. All right, and we can see this right here. Y equals 1 over c times f of x shrinks vertically by a factor of c. And it's this space in the graph. Okay, how about we see that on the graphing calculator, and that's okay, let me do 1/2 instead. Second, square root of x. Well, because of this 1/2, the graph that we will see in red, we would expect to see smashed graph with respect to the graph in blue. Let's see if that is the case. Okay, and it is. All right. So the graphing calculator here confirms what we are looking from the notes on the textbook here. Actually, these notes are straight out of the textbook, by the way. What else do we have? Okay, whenever we multiply a function by a number, but now outside of the parentheses, or radical or exponential, but rather inside, we will go about the reverse and shrink horizontally. So shrink horizontally by a factor of c. And let me use the same example. That one is going to be over here. Well, it's not on the graphs right here, so that's why I'm going to use instead the graphing calculator. So y equals to delete. So instead of having the square root of x, I'm going to have the square root of 2x. Well, so in this case, according with the information, we should expect to have a graph that is shrinked horizontally, right? Let's see if that's the case. Right? So it's gonna shrink horizontally, but at the same time is stretched vertically. So that's what happens with shrinkings and stretchings. And the other pieces of information, well, this would be the opposite, right? It would be stretched horizontally. Let's see how that works. So that's delete. I'm gonna do x over 2. And see how this red graph is stretched horizontally, or at the same time is also shrank. It's being shrank vertically. It's either way to see it. It's fine. Okay. What about this? Okay, what's next? Oh, the next is the reflections. And well, we already saw about this when we change the sign of a function. Changing the sign of in front of a function reflects the graph about the x-axis. That is, reflect about the x-axis. In this case, well, you can see the x-axis as a mirror. And do you see how this graph, the original graph of f of x, which is drawn in black, versus the one in orange that I highlighted in green, aren't those two graphs reflected about the x-axis? So this is the picture of what happens when we change the sign of the function. But when we change the sign of the x's, on the other hand, we're getting the opposite in sign of the x values. That means we get a function that is reflected about the y-axis. And the picture here is this. Okay, reflect about the y-axis. So that's the y equals negative f of x. And again, we can think of the y-axis as a mirror and focus on these two graphs. They are reflections about that y-axis. Okay. All right. So this is a really brief summary of all the different transformations that a function f of x goes through. It's important to keep in mind at least the most basics like horizontal and vertical, and the reflections. Typically, when it comes to the stretching and shrinking, we don't use those very often, but it's actually good to keep those in mind as well. All right, so how about we do an exercise, all right, and see the transformations of the graphs. All right, so this is what we're going to do. We're going to match each of the graphs. Of course, okay, let me highlight the parent graph, the basic graph. So y equals the square root of x. It's going to be this is the original graph. All right. Let's look at y equals the square root of x minus 2. Which of these remaining 5 graphs represent the shifting here? And well, actually, let me label them. Okay, so this is A, B, C, D, E, and F. We already saw that this is A. All right, that's the given. Okay, so the second function, y equals square root of x minus 2. Which graph will be representing that function? B. Well, so this negative 2, which be careful with the negative 2 inside of the radical. When it's outside of the radical or outside of parentheses or outside of the exponential, that means vertical shifting, and because of the negative, that means it's going to go down to units, okay? Okay, what about y equals the square root of x minus 2? Yes? Mm-hmm. That's going to be letter C. It's 2 units to the right, right? So C. And well, okay, the next one, y equals the square root of negative x inside. F. F. Does that look like F? Yes, looks like F. So when we change the sign of the x's inside parentheses, in exponents or radicals in this case, that changes the sign of the x's. I mean that they're sending to the opposite side. And y equals to root of x. What is that going to do? If that looks like E, it's gonna stretch it vertically. Yep, that's E. And well, the last, we only have one, which is going to be D. All right, it's a reflection about the x-axis. All right, let's see what else do we have. When it comes to transformations, sometimes we will be given a function in the very particular case, quadratic functions. Well, of course, so what do we have here? Number one, y equals x squared plus 6x plus 10. Well, before learning about transformations, you first learned about graphing functions by plotting points, right? By having a table of values of x's and to find the values of y. However, it may not be very practical to do that in this case because, well, the graph of a quadratic function is going to be a parabola, but we don't have an idea of what portion will we get if we did that, because typically when we do a table of values, we do 0, 1, 2, 3, 4, right? We don't put negative values in many cases. Well, in this case, if we had this 0 to 4, for example, we may get only one side of the tails of the parabola, and we may not see a really clear picture. So in this case, we are going to use transformations to graph this function. But well, this function is given in polynomial form. We need to write it in the other form, in the vertex form. It's called the vertex form, and the vertex form actually shows explicitly the transformations that we're going to use to plot the graph. Because, okay, number one, we're going to start with the graph of the parabola y equals x squared. 0 squared, 1 squared, 2 squared. Alright, so that's the original parabola y equals x squared, right? This is our starting point, and then from there we're going to shift. But again, the form of this trinomial is not one that we can use shifts. All right, so we are going to write it in vertex form. Any ideas? Anybody remember what do we do to write trinomial form into vertex form? Yes.
Completing the square.
Completing the square. So what do we do to complete the square? Well, if we had this trinomial, for example, y equals x squared plus 6x plus 9, for example. This is a perfect square trinomial that can be factored this way. X plus 3, quantity squared, that is the square root of the first term, the sine of the middle term, and the square root of the second term, the square root of the second term, and the whole quantity squared. That is, if you expand this binomial, you should get back to this.
That's fine.
But in this case, this is not a perfect square trinomial because in the first place, this independent term right here is not a perfect square. So, well, we need to add and subtract a magical mystery number that completes the square. Well, so what am I talking about? Well, so that's x squared plus 6x plus blank That blank is the magical mystery number that completes the square, and then plus 10. But the thing is here, if I add a number to complete the square, I would be altering the integrity of the original expression. So we cannot just add a number. So if we add a number, we need to do the opposite as well, which is to subtract that number. How do we find that magical mystery number?
1.
It's 1? Okay, so to find that magical mystery number, what we do is divide the middle coefficient by 2 and then square. So m, magical mystery number, and that's a 6/2 quantity squared. That's how we complete the square. So this is 6/2, which is 3, and then 3 squared, which is 9 and 9. Alright, so we add 9, subtract 9. Now, these first 3 terms are going to comprise that perfect square trinomial. That's going to be x plus 3 quantity squared, and 10 minus 9, that's a plus 1. Alright, and what did we just do? We just wrote the trinomial function in terms of vertex form notation. And well, from here we can easily see we can easily see that our parent graph, the parent function is y equals to x squared. Are you guys following me here? Yes? Okay, so let's describe all the transformations of this function. So what is this plus 3 telling us to do? 3 units to the left, and what about this plus 1? 1 up. So I'm going to go from the vertex, which is 0, 0, I'm going to move 1, 2, 3, and 1 up. And then from there, graph the remaining points. So 1, 1, 1, 2, 3, 4. And that's our shifted function. Alright? Well, now, if you wanted to plot this function using a table of values, well, you now have a picture so you now have a picture so you can choose the convenient values. I would graph the function from -5 to maybe -1 or 0. However, do you see what would have happened if we made a table from 0 to 5? We would have gotten just like almost a straight line on that side of the first quadrant. We wouldn't have been able to see the parabolic shape of the actual function. Do you see the issues with using tables of plotting points by tables? So in this case, it's important. That's why it's important to know the properties of quadratic functions, quadratic equations. How do we go from trinomial form to vertex form? And that's actually going to give us a better picture with the vertex form, because we can easily see what the transformations are. 1, -1, 2, 3, -3, comma 1. All right. Let's look at another example. So sketch the graph of the function y equals absolute value of x squared minus 1. All right. Y equals x squared minus 1. So, well, how about we start with the parent graph of y equals x squared. This is the usual parabola, right? Okay, and then from here, what is that -1 going to do to shift 1 unit down, right? So.
Wait, why is it
Right.
Right, it's right. Why is it 1 down?
Oh, okay. Yeah, so, okay. Roadmap. Y equals x squared. Y equals x squared minus 1. And then absolute value of x squared minus. So what we're gonna, I forgot to mention that we're gonna do one transformation at a time, starting with the core function and then going from inside to outside. Okay? Well, so we start with the graph of the parabola, then we shifted 1 unit down. Right, that negative outside means down. All right. Okay, and then we are going to take the absolute value of that expression. Okay, what does the absolute value mean in this case?
And the output will always be positive.
Everything that is negative becomes positive. So what part of the graph is negative in this case?
The space between -1
The space, everything between the interval -1 to 1, which is what I will highlight. All right, okay, first of all, let me keep labeling just so you can see what am I doing here. So this is y equals x squared. This is y equals x squared minus 1, and then y equals the absolute value of the whole thing. Whatever is negative, it's going to turn into basically upside down to be represented positive. So this is going to look like this. All right. Do we have any negative quantities in here? No. So I think this represents very well the absolute value of a function. All right. Okay, so what else can we do with functions besides doing shiftings and transformations?
Why did we shift down and not towards the right? Why did we shift down and not towards the right? Why did we shift vertically downwards?
So, well, in this case, we did first the shifting down, and then we do the turning to absolute value.
He's asking why you didn't shift it to the left because it's inside of the.
Oh, yes. So, I know it would have been a little crazy to think about the absolute value function, which is like the V shape, but then from there, how do we describe the V-shaped function but having a square inside? That would have been more complicated to do rather than this. So instead, what I did is to break up the function going from the simplest in this order, shifted down 1 unit, and then take the absolute value in the end. Actually, when we look at combinations of functions and when we look at compositions, which is next, this is going to make more sense why I did it this way instead. So let's see. Combinations of functions, that's going to take us back again to intermediate algebra. So you can do a bunch of operations with functions. You can add to functions, subtract to functions, find the product between two functions or the quotient, and the one that we will be interested the most, composition functions. That is when we have a function and we evaluate it at another function, not at a number, but rather at another function. And well, so as an example, so if we have two functions, y equals to the square root of x, well, actually, let me relabel this. This should have been f and g, just so we are consistent with the notation here. Well, so they're asking us to do the composition in certain direction. By the way, not all functions, some functions would give you the same result when you compose them regardless of the order, but that only happens when we have inverse functions of one another, like e to the ln or ln of e to the x. Those are the only cases. In this case, well, you'll see what are we going to get. So f, this little circle right here means we read it f bubble or f composite g. That's f evaluated at g of x. Now, in this case, which one is the function f? Square root of x. That means this is the square root of g of x. All right. And finally, what's g of x?
G or square root of 2 minus x.
Square root of 2 minus x. And of course, we can simplify this function a bit further because we can we can rewrite the inside function 2 minus x to the 1/2, and then the outermost radical is also a 1/2. Now, what do we do when we have power of another power? Multiply the power, and in this case that's going to give us 2 minus x to the 1/4. And going back to radical notation, which root is going to be this one? The 4th root. Recall that by properties of radicals, the denominator of a rational exponent is the index of the radical. So that's the 4th root, 2 minus x. So that's a new function that we obtained by composing two functions together. And well, they're also asking us to find the domain. And from last time, from the guidelines of the domain, well, we have a radical function of an even index. Is that the case, that it's all real numbers? Or how will we find the domain? Any ideas? Yes.
All numbers greater than 2.
Yes, well, but how do we get that it's greater than 2? What's the first thing we do?
We usually check like 2 minus x should be greater than
Exactly, so that means from here 2 minus x, first of all, has to be greater than 0, because the radical function of even index only accepts functions, positive values and 0, not negative values. When we solve this inequality, we get negative x greater than or equal to 2, but when we divide both sides by -1, what happens? It reverses the inequality, the direction of the inequality symbol. So, alright, so be careful when setting up the domain for this. First, set the expression greater than or equal to 0, and then from there, just solve the inequality. And careful with those properties of inequalities, especially that one in which we multiply, divide by a negative number. Yes?
It's supposed to be -2.
Yes. -2.
Like,
Right here?
It should be greater than 2 positive
Subtract
sign.
2 and then equal the sign is supposed to be positive.
Okay, so whoa, that's true. Negative, yeah. Thank you. And in interval notation, negative infinity to 2. Do we agree with this answer? Yes? Bracket, right? Bracket, because it's inclusive for the endpoint. Okay, let's do the composition the other way, in the other direction. Well, so in this case, this is going to be the g function evaluated at f of x. So number one, what's the g function in this case? So that's the square root of 2 minus x. Alright, minus, in this case, f of x. And what's f of x in here? 2 minus the square root of x. Okay, we need to be very careful when they're asking us for the domain of an overall composite functions, because, well, in the previous example I didn't do anything about, because, well, number one, what's the restriction for 2 minus x? Do we really have any restrictions? That's like a polynomial that is all real numbers, so that's about it. But what about in this case? We are evaluating a new function using another function that already comes restricted in domain. What's the restriction for the square root of x? What's the domain of that function?
Greater than or equal to 0.
Greater than or equal to 0, right? So x greater than or equal to 0, that's for the square root of x. Alright? And well, so this is the new function, the new composite function, which, by the way, this function doesn't look the same as that function. So that's why order matters when it comes to composition. We may get two totally different functions. And well, this is an example that illustrates the idea. But now, to set up, or rather to find the domain of this function, we need to set the radicand, that is the quantity inside of the radical, greater than or equal to 0, and solve for the variable x. So number one, so negative root of x greater than or equal to negative 2, and then divide both sides by negative 1. That gives us square root of x positive 2, but reverses the inequality symbol. And then to get x by itself, just square both sides, so x less than or equal to 4. So what am I talking about? That means that in this case we need to have a look at two different sets. Remember how we combined two functions together? Well, it was three functions together in the last example last time, and then we found the intersection of those sets. We're going to do the same here. So for the first, which is the restricted function, that's the square root of x. So this is 0, this is 0, right? So let me do blue. So that's the domain of the square root of x. Alright? And then we have x to be all real numbers below 4. In this case, oops. If 4 is here, all the numbers below are these numbers, right? Any number below or equal to 4. Well, so what happens when we put these two sets together? So suppose you can do like a sandwich with those two sets and find the intersection. So we will be looking at the overlaps of those two sets.
The intersection between 0 and 4.
0 and 4 are going to be the overlaps. Do we all agree with that?
Yes.
Yes? Over here? Yes? Okay, so that's the domain. Zero and 4. Alright? As a note, the overlaps. Alright? Okay, what else can we do? Let's see. What about, so the next topic here is, okay, performing compositions of functions. So, well, in the previous couple of examples, we did a composition of only two functions. In this case, we are going to do a composition of three functions, and this is something that we need to be sharp on, because when it comes to finding derivatives of functions using the chain rule, we need to be able to identify the different layers that a function is comprised of. So in this case, what we're going to do, we're going to create the function first. So that means whenever we see this notation here, f bubble with g bubble at the same time with h, this means f evaluated at g, which is also evaluated at h.
So doesn't the bubble just mean multiplied?
No, it means composition. It means composition. The multiplication would be just a little dot.
Okay.
But this circle right here means to compose a function, to evaluate a function with another function. Well, so what are we going to do in this case? So we are going to go this time inside out. Well, what's the h function?
X plus 3.
The x plus 3. So I'm going to go f of g of x plus 3. What's the g function?
X to the power of 10.
So that means that this x to the power of 10, so whatever for at the g function, whatever I see the letter x, we will replace it with x plus 3. All right?
We get the power of 10 as well.
And this is f of x plus 3 to the 10th power. And now the last piece of composition is for onto the function f. So that means the function f will be evaluated at x plus 3, which means wherever we see the letter x on the function f, we will plug in x minus 3. That is x minus 3 to the 10th power over
Why are you plugging in x minus 3?
to the 10th power, because it
Why is minus 3?
it's plus 3 and x plus 3 to the 10 plus 1. So that'll be the new composite function. Right? Of course, I mean we can even make it more interesting by adding it. I don't know. How about we add one more? What about G bubble F bubble G bubble H? All right. Well, we already did the composition of these three, so we don't have to do the whole thing. So that'll be G evaluated at this x minus 3.
It's x plus
Oh, plus 3 again. Yeah, again. Thank you. Over x plus 3 to the 10th plus 1. But what's our function G? Isn't that to the 10th power?
yes, but then you do for x.
X plus 3 to the 10th over x plus 3 to the 10th plus 1, the whole thing to the 10th power. Do you see this pattern of how we compose functions? We have like an inner layer and then an outer layer and then an even outer layer and an outermost layer. So for this, you may want to think of, have you seen those nested dolls, the babushka dolls? Well, I have this. Well, these are not the babushka dolls. These are like Star Wars ones. Well, they're very tiny. Hopefully you guys can see it. So what do we have? We have an outermost function, right? Then we have an innermost function. So the outermost function would represent this quantity. Where's my hand? Where did I? Oh, here. Would represent the function to the 10th power. Do we agree? Then we have an inner function, the stormtrooper here, that represents this whole quotient. Alright? Well, then we're going to get another function that's inside. Alright? And that represents the x plus 3 to the 10, the x plus 3 to the 10, and even the very inner layer function. Let me highlight it so you can see it. The very inner function, which is the x plus 3. So that's how we compose functions. We can have this perspective here when it comes to composition functions. So guys, we're going to go back to this later when we go deep into calculus, in particular when we do the chain rule, because we're going to take derivatives of outer, innermost, well, depending on how many layers do we have for a function. All right? And of course, it's important to know how to do this process, the backwards process. So given a function, cosine squared of x plus 9, what are the functions f, g, and h such that they give us the composition f? Okay? So let's go about that. It would be good to rewrite the function in a different way. So how about big F? Big F of x. Instead, I'm going to write it as cosine x plus 9. But do we agree that this cosine squared is the same as writing it this way? Are we good? Okay. I think if we write it this way, it's easier to see the different layers the function is composed of. So we have an outermost layer, which is something squared. Agree? An inner layer, which is cosine. And an innermost layer, which is x plus 9. X squared, cosine, x plus 3. That is little f equals x squared, little g equals cosine, and little h equals x plus 9. Do the composition f bubble g bubble h. So we will start with the squared and have this composite function. All right. But again, it's we're gonna go about this later when we go to the chain rule I believe, well,